In this video, we will discuss how derivatives affect the shape of a graph, specifically the graph of our function. We have two learning objectives. First, to use the first derivative to identify intervals of increasing or decreasing, and also to use a second derivative to identify intervals of concavity for concave up and concave down. Looking at our vocabulary, you can see, of course, how the vocabulary ties directly into the learning objectives. And our key terms are the tests which will allow us to achieve our learning objectives. So let's start off with some of the words you need to know. A function is increasing on an interval if, for any two numbers, x1 and x2 in the interval, x1 less than x2 implies f of x1 is less than f of x2. Okay, so what's that talking about? Fairly straightforward. If you have a number that's on the left, it means their height is going to be lower. So if we were looking, here's x1 and here's x2. x1 is to the left, less than x1. If we then had, well, I should use tick marks there, not dots. But if we had a piece here, mixed up the piece there, our height f of x1 is lower than the height f of x2. Huge surprise, right, guys? That when you're looking at it, this is increasing. And we have a similar criteria for decreasing. Of course, decreasing would look like this, with the requirement that if you have a point on the left, x1 is to the left of x2, that will cause the height of x1 to be higher than the height, the function value of x2. This is just a quick way of writing out this very intuitive graphical understanding algebraically. One of our key learning objectives is to identify the intervals where you have an increasing or decreasing function. Basically, if we have a graph that looks like this, where is it increasing, where is it decreasing? In your previous classes, you would have already looked at it and said, well, visually, I can see that it's increasing on this x interval, and it's increasing on this x interval, and therefore decreasing here and decreasing there. Graphically, we can do that very, very quickly. Very easy if you already have the graph. But what are the actual numbers? What are the numbers that split it up? What are the numbers that create your intervals of increasing and decreasing? And also, how do you find those numbers? Some things that should jump out at you just from this graph. Take a look at everywhere they split up and pay attention to the derivatives of those points. Derivative is 0, derivative is 0, derivative is 0. That's not an accident. In our previous lessons, you remember searching for the critical numbers, the places where the derivative is equal to 0, or the places the derivative does not exist. Our critical values are what will help us locate the intervals of increasing or decreasing. And so let's do our first example. Find the open intervals on which f of x equals x cubed minus 4x squared is increasing or decreasing. Well, we have a couple of choices. If we want to do it graphically, yes, we know the calculator can do it. We can come in and type in x to the third minus 4x squared. I believe that was the correct function. And we can hit graph. And we would be able to use the calculator's minimum and maximum functions. We want a minimum here and there. And so there we go. We have an approximation. The minimum is occurring at 2.67. It is a minimum of negative 9.48. Those are approximations. They are not perfect. We know that the calculator gives us rounded answers. If we wanted to get a maximum, we know that the calculator can do this very, very rapidly and say, okay, we have a maximum at the point 0, 0. Once again, these are pieces that we're looking at and saying, we know the calculator is awesome, we know that it can do a lot, but we don't want to use the calculator for absolutely everything. The calculator is a tool to help you do things more quickly, but if you can't do it on your own without a calculator, you've got problems. You should know how to do it anyway. Well, the major feature that we had to look at is coming back to this piece. We had these points where it changed from increasing to decreasing based on the idea that we had the critical values. Let's start there. Let's figure out the critical values of this function. So f prime of x equals 3x squared minus 8x. Critical values are where the derivative equals 0 or does not exist, and this derivative is a polynomial, so it will exist everywhere. The only thing we need to concern ourselves with is where does the derivative actually equal 0? We could factor out an x to give us 3x minus 8, and then by the zero product property, we would know that x is equal to 0, or 3x minus 8 equals 0, and simply solving those, we get the two critical values, x equals 0, or x is equal to 8/3, which we know is 2 2/3. Again, noting those were the x values, so it's matching what the calculator gave us. We're just even more precise because we have 2/3 instead of 0.67. Well, where this is beneficial for us is we know the overall function is continuous. And this tells us that these are the places where potentially, not a guarantee, but potentially, we could, or rather, bleh, these are the locations where we have a horizontal tangent line. With a horizontal tangent line, it leads us to the possibility that we could have a function changing. I know that's vague. I'll be a little bit more clear coming up in a second. But the important characteristic I do want to note is the critical values take the x-axis and they chop it up in the way that I did here. If we were to cut up the x-axis, we would have everything starting over from negative infinity and include absolutely everything up to the smallest critical value. In this instance, it's 0. We could then go from 0 to the next critical value, which is 8/3. We would then go from 8/3 all the way up to positive infinity. One of the nice consequences of having a continuous function is the understanding that on every single one of these intervals, on each piece, whether it's the first interval, whether it's the second interval, or the third, on the entire interval, this entire piece will be increasing, or the entire interval will be decreasing. Everything on that interval. Same thing here. Each of the critical values will allow us to find locations where the interval is either increasing or decreasing. Based on the graph that we already did, sorry, wrong button, we know we can see the increasing is the first interval, decreasing on the second, increasing on the third. So, increasing, decreasing. What we would like to be able to do is put in some extra algebraic criteria that would say, how do we know this is actually correct? How do we know that it's increasing, then decreasing, then increasing, without actually needing to revert to the calculator every single time. And the tool we have for it is the first derivative test. One of the main things worth noting is when you have a function that is increasing, like here, if you look at any single point in the interval, that tangent has positive slope. Look at another one. The tangent has positive slope. Pick another tangent. It has positive slope. Whenever you have positive slope, you get an increasing function. That's immensely relevant because positive slope is the exact same thing as saying the derivative is greater than 0. Wherever the derivative is greater than 0, we get positive slope. Positive slope gives us increasing function. Of course, on the other side of that is if you have a decreasing function. A decreasing function, you will note, has a whole bunch of negative sloped tangent lines. Same piece. If the derivative is negative, that means we have negative slope, which means we have a decreasing function. The first derivative test takes advantage of that. Specifically, if we want to know if a graph will actually have a local maximum or a local minimum, this is a tool that we can use. You'll remember in our previous work, we encountered problems where we could say, like here, we have a horizontal tangent line, or this one. We have horizontal tangent lines where our critical value was 0, but they did not translate into a local maximum or a local minimum. Before, if we wanted to know that if we actually had a maximum or a minimum, we needed to go through and start picking actual function values, pick an x value, figure out its f of x value, and then say, well, this is a height of 12, this is a height of 10, this is a height of 8, therefore there's no maximum or minimum. Or we had pieces that would say, this is a height of 12, this is a height of 8, and this one is a height of 11. That means this was a local minimum. The critical values gave us places where the local maximum or local minimum might be. The first derivative test will give us a guarantee, is it here, yes, no, or more investigation. Specifically, if we have a function that changes from increasing over to decreasing, the only way you can go from going up to going down is if you reach a peak, so it gives us a local maximum. Well, please note, that is saying the derivative changes from positive to negative. If your derivative changes locations from positive to negative, that is a local maximum. And if you have the derivative change from being negative into being positive, if it changes from decreasing to increasing, the only way you get that is with a local minimum. That's what the first derivative test tells us. It also tells us that if we are taking and saying, okay, it's increasing, so we have a positive derivative, but then it stays increasing, even though we had this point where we had the horizontal tangent line, it's not a maximum or minimum. And here's one type of problem that we can use for it. Find the relative extrema, also called the local extrema, for the function 1/2 x minus sine of x, only in the interval from 0 to 2 pi. Okay, so without using the calculator, because of course we don't just want to rely on the calculator for everything, the first derivative test tells us, number 1, find the critical values. That's taking our derivative. That's 1/2 minus cosine of x. Since this is an algebraic function of a sum of a constant and a trig function, we know this is continuous. Since it's continuous, we know also, well, we also know it's differentiable. Since this derivative will exist everywhere, the only thing we have to worry about is where it equals 0. So when is the cosine of x equal to 1/2? When we find that value, or values possibly, in the interval from 0 to 2 pi, we will have our critical values. So basically, we're just saying take the inverse cosine of each value, and we will get inverse cosine of 1/2. This is a part where we could use our calculators, or we could wind up trying to use the unit circle. Though the unit circle wouldn't be immensely beneficial, we would wind up with 1.0472 approximately for our interval. In fact, to get this number, I actually did use the calculator. You also got to be careful though, because we were looking for values in the interval from 0 to 2 pi. 0, of course, is 0, but 2 pi is approximately 6.28. We do need to consider a quick sketch of the unit circle. And note, this angle is our 1.0472 radians, because that's when we would have 1/2. We also have the same value if we were to drop straight down and identify this angle is still in our circle for 0 to 2 pi. So if we took 2 pi minus the 1.0472, we would get another angle x that still fits the same criteria. And it's actually 5.2360, rounded to 4 decimal places. Where this is helpful for us is these will cut up the entire x-axis from 0 to 2 pi, because the only ones we care about are from 0 to 2 pi, but it would work in general for other functions, into 3 pieces. And the big advantage to, okay, gotta move these, move it. Come on. Okay. And then 5.2360 up to 2 pi. All right, finally coming back to what I was trying to say. We know every one of these intervals is either increasing or decreasing, because we found the only places where we could possibly change from increasing or decreasing. That's what our critical values do for us. Since these are the only places, we just need to ask ourselves the question, is the derivative here positive or negative? And same thing for each interval. If the derivative is negative, we have a decreasing function. So we are actually allowed to pick absolutely any value we want in the interval. Generally speaking, pick easy ones. What I would like to consider, 1 is in the interval from 0 to 1.04, and from 1 to 5.2, that would be a number like, how about pi over 2? Pi over 2 we know is approximately 1.57. And from here, we could say f prime of 6. But you can pick any value you want. We do not care which number you pick, as long as you pick one number from somewhere in the interval. Frankly, if you really wanted to, you could pick f prime of 2. You could pick f prime of whatever. And more generally here, we do not even care what the actual value is. The only thing that we're concerned about is when we take the derivative, is it positive or is it negative? Because positive versus negative will tell us if it's an increasing or if it's decreasing for this particular interval. In an effort to save some time, we don't need to do a whole lot. So let's take a look and say, with our derivative, 1/2 minus cosine of x. And one of the big pieces I'm going to be looking at is my unit circle that I had over here. And in order to help make it a little bit clearer, I would like to bring it down over this way and say, where's my circle? Okay, so here we go. I already know that this is the spot where my cosine is equal to 1/2. And this is my 1.04 degree angle, so if I am picking a value of 1, that's an angle that's a little bit smaller than my 1.04, which tells me my cosine is a little bit bigger than 1/2. Since the derivative is 1/2 subtract cosine, well, if I'm subtracting something that's a little bit bigger than 1/2, that tells me this is negative. And I don't even care what the number is. I know it's negative. Moving on to f prime of pi over 2. Pi over 2 is here. So I should change my color here. I'll switch it to blue for the second one. My cosine is 0. So for this one, it's 1/2 subtract 0, which would be a positive. And then going to f prime of 6, we know this is my other one. Or rather, we could say use green on this one. 6 radians would be about here. And so if I'm coming up, my cosine is the x coordinate. That's longer than 1/2. So like the first interval, I have 1/2 minus some number that's bigger than 1/2. I can recognize that this will be a negative. Well, this is the important characteristic to note then about the first derivative test. We had a function that had a negative slope, then changed to a positive slope, then changed to a negative slope. That would tell us that this point where x is equal to 1.0472 and yellow, this piece, based on the fact that it's changing from negative to positive, this interval was I wrote that wrong. This, come on, Fry. Because it changed from negative to positive, it tells us this was an interval because it changed from negative to positive. It tells us that this x value of 1.04 was a local minimum. Coming over, because it changed from positive to negative, that's going from a positive slope over to a negative slope, that would identify that the other one was a local minimum. Oh, a local maximum. Come on, can't even speak correctly. So, two pieces, finally summing this all up. This is an interval where the function was decreasing. It was decreasing because of the negative slope in the derivative. The same thing is true here. The negative slope in the derivative meant from 5.236 over to 2 pi, it was a decreasing function. The original function was decreasing. The area in the middle, where we had positive slope, this was an increasing interval. The first derivative could be used to help us identify the intervals of increasing and decreasing just by paying attention to the derivative. But if we also pay attention to where the derivative changes from negative to positive, we could identify that when you change from decreasing to increasing, you get a local minimum. And where you change from an increasing function to a decreasing function, you get a local maximum. That's the sum of the first derivative test. Okay, so taking advantage of some information. Sketch a possible graph that would fit these conditions. First things first, always put down the points. Points are guaranteed spots where you will need to connect the dots. It's just connecting the dots in an appropriate manner. So f of 0 equals 0, x equals 0, y equals 0. F of 2 equals 2. 1, 2, 1, 2. It tells us when x is equal to 2, y is equal to 2. 3, 4, 3, 4, 5. So we are now told when x is equal to 4, y is equal to 5. So 4 comes up to 5. And if those were the only requirements we had, only those three things in yellow, bam, we've got something really fast to meet 3 criteria. But there are others. Our next part is to say the derivative of the function is 0 at x equals 0. And the derivative is also, so the derivative at x equals 0 and the derivative at 4 are both equal to 0. So it tells us at 0 and at 4 we have horizontal tangent lines. So basically, we've got to kind of fill it in and say horizontal tangent line. And when x is equal to 4, 1, 2, 3, 4, we have a horizontal tangent line. So we have to kind of fill in this type of behavior where it flattens off. You'll note, by having that, this is what would prevent us from saying something like I had before, because then our tangent line is not 0, and the tangent line is not 0. So the conditions in red eliminated the first quick guess sketch we had. Continuing further, f prime of x is greater than 0. The derivative is positive, so that tells us it's an increasing function for 0 to 4. Okay, so we would say this has to be horizontal tangent line. So something like here, where we could have the horizontal tangent and an increasing function from 0 to 4. But then I'm building in potentially a point where we could have it change its increasing or decreasing. We then have f prime of x is less than 0. That tells us it's a decreasing function for x is less than 0. Okay, we've got that. Decreasing all the way down, horizontal tangent line where we would have a local minimum. And it's also decreasing for x is greater than 4. We've got that as well, giving us a local maximum at x equals 4. And there we go. We have one possible sketch. One of the things we would like to note You see this part right about here in the middle of my graph? This almost looks like a parabola being put right here. And this looks like a part where we'd almost have a parabola going down like this part. And I'm using a parabola to almost think of them as bowl shapes. When I'm looking at these two particular sections, you see how it's kind of a bowl going upward and a bowl going downward? Well, in one of your previous classes, you would have talked about the end behavior model. Specifically, you would have talked about a parabola opening upward or opening downward. You did that specifically with parabolas. In calculus, we take it further than just a parabola and say, with other shapes, when do they open upward and when do they open downward? Where are the places where that happens? And that is where we get our definitions for concave up and concave down. In particular, if we're looking at this one, start considering where all of the tangent lines are. If I were to take this type of graph and say, okay, tangent line. You notice the graph is below the tangent line. And I could pick another tangent line. The graph is still underneath. And pick a third one. The graph is underneath. Pick a fourth one. No matter where I'm drawing these tangent lines, in every instance when I'm drawing the tangent line, the graph is still below the tangents. When this type of issue happens, it's an example of a concave downward graph. If you think in terms of a parabola, you could see almost like this is a parabola that is opening downward. Or in this instance, a couple of parabolas that open downward. Basically, the bowl is tipped upside down. It's also possible that we could encounter graphs that are concave upward. Instead of having every single tangent be underneath or above it, we could have a graph that would look, and I'm just going to pick this one, this way. So when we start looking at each of the tangents, there's our tangent. This time, the graph is above the tangents. Another tangent, another tangent, another tangent. Every single time we draw a tangent, we always get the graph is above the tangents. This is our definition for concave upward. Being able to find places where we have concave up and concave down is another crucial part of our learning objectives. Please remember, our second learning objective was to be able to find the intervals of concavity, where it's concave up and concave down. Well, once again, we know that we could go back and look at a graph, and I got rid of it, but if we had x to the third minus 4x squared, we could look at it and say, where do we wind up having kind of these bowl shapes? And looking at it, we could see there's kind of a bowl on the left and there's a bowl on the right. But where in the middle, there's somewhere around here where it seems like it's going to join and say, it switches somewhere in here from being a bowl facing down for concave down and a bowl facing up for concave up. We've got somewhere in there that's creating an issue like this. But where is it? How do we find it? And that's going to be one of our issues here. Sketch a possible graph that's going to satisfy these given conditions. Well, a lot of them we already had, specifically this piece right here. So I'm going to quickly repeat some of them. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, 5. F of 0 equals 0, f of 2 equals 2, f of 4 equals 5, f prime of 0, f prime of 4 has to be decreasing, has to be increasing, has to be decreasing, has to be increasing. And so the big question that we're going to run into now is, how does the rest of this connect? Here are the new pieces. The second derivative is greater than 0. When you have the second derivative is positive, that's when you get a graph that is concave up. So this is concave up for x is less than 2. That tells us on this part it needs to have a bowl shape. So if I picked something like this to say it's still an increasing function, but would you describe this as one big bowl coming up? You can see at this part it almost looks like in this particular area right there we have concave down. Especially when we consider its tangent line, we can see it. So having this type of graph violates my concave requirement. Instead of coming down like this, it would have to connect more like that. We still have the minimum, we still have increasing, we still have decreasing, we still have all the points. It's just how quickly it's reaching this other set of points. Coming over to the second part, f double prime of x is less than 0. That's a way of saying that it needs to be concave down. So once again, I would not be able to take a piece and say this is increasing and connect it up like this, because this is not concave down. If we looked at the tangent, it violates our rule for concavity. Because we need to have this concave down part, it tells us this has to connect upward in this type of manner. Not coming up like that, but coming up more like on a hill. And so we get a more accurate representation. When you look at this particular one, this seems very similar to the one I had last time, but pay attention. This is the point where it changed from concave up to concave down. That occurred at the x value of 2. In the last one, that place where it changed from concave up to concave down was closer to 2 1/4. It may not seem like that's such a big deal, but when you're trying to create an accurate graph, it is. And it, especially when you're working with applied problems, it throws things off if you're not a bit more careful with it. So there we go. You'll note that was a way that we could identify our intervals of increasing and decreasing using the first derivative test and then setting up those test intervals. We then use the second derivative to say where is it concave up and where is it concave down. The second derivative test is, for a lot of people, they like it better than the first derivative test. Simply because, I mean, let's face it, when I went through and did these little test intervals where I was doing this part, was it really, really clear? I know that I did not do a particularly effective job of explaining it well, but did it really make that much sense? The second derivative test is in many ways a simpler, more efficient method. It does require you to take a second derivative, so in that regard, perhaps it's more work, it just depends on your preference. You could use either one, as long as the directions don't specifically say use this method, you could pick. But the second derivative test is a way of using 2 derivatives instead of 1 to find your intervals of increasing and decreasing. It's a way of figuring out where you would have a local minimum or a local maximum. So for this one, we're not looking for the intervals of increasing or decreasing, though we'll probably get that along the way. We just want to find the local extrema. So first derivative, that would be 4x to the third minus 12x squared. In order to find the possible places for a local minimum and a local maximum, we need to have the first derivative be equal to 0. So we still need to go through and solve when is the first derivative equal to 0. Running through the algebra quickly, we could factor out 4x squared, leaving behind x minus 3. And when we solve that, we get two values, x equals 0 or x equals 3. Please note, finding the critical values will chop up our x-axis from negative infinity up to 0, and then from 0 to 3, and then from 3 to infinity. If we wanted to, we could figure out, using the first derivative test, if the first derivative is greater than 0, or if the first derivative is greater than 0, or greater than 0, we could do that for each individual part and use the first derivative test. But here's where the second derivative test is beneficial. We don't need to go through and pick a crap load of test values like this. We could use concavity. Because if the graph is concave up on this interval, well, if it's concave up, it means it looks like that. Well, if we have it concave up and then it bottoms off at the horizontal tangent line, what does it tell you? This point of 0 then would have to be a local minimum. Or if we had a part where we were looking at it and we had our critical value, but then we have it be concave down, well, that tells us it's concave down. That tells us it's reaching a local maximum because it needs to be continuing concave downward. If it wound up with a piece where it didn't look like this, or if it didn't look like this one, well, blue is concave down, red is concave up. Is it possible that we could have something else going on where we have a horizontal tangent line, but we don't really have concavity? Well, it's entirely possible that it could be just a flat horizontal line for our second derivative. If the second derivative was just flat out completely and totally horizontal, this test fails. More generally, you notice how it says greater than and less than? Make sure that you don't have second derivative be equal to 0, because if you wind up with the second derivative equals 0 for this f prime, double prime of c, then the test fails and you have to wind up using the first derivative test anyway. So anyhow, backing this part up. Oh, too much. Point is, we have our intervals, and we have located the places where we have possible extrema. To find out if they actually are, we will now take the second derivative. Second derivative is 12x minus, or 12x squared minus 12x. I'm sorry, 24x. And we want to know where is the second derivative positive, where is the second derivative negative. Positive and negative is going to play a role with where it changes around 0. So solving where it equals 0, that's telling us 12x, x minus 2. So possible points of x equals 0 or x equals 2. This is telling us our graph is overall going to be, these are the places where we could change, 0 and 2 are the places where we could change from concave up to concave down, or they are the places where we have concave, concave up or concave down. But all we really need to be able to do is say, at this point of 0, what is the second derivative? Double prime of 0, well, 0 squared minus 0. The second derivative here is 0, and our test fails. This test will not let us know if we had a local maximum or a local minimum at 0. We would need to do more investigation using the first derivative test. If we tried the other one, though, plugging in 3 and 3, 3 squared is 9. 9 times 12 is 108. And so, f double prime of 3 is 108 minus 24 times 3 is 72. We wind up with 36, which is positive. That's beneficial for us because it tells us that this value of 3, because it's a critical value, and because the derivative is, the second derivative is less than 0, this point of 3 is a local maximum in the original function. For 0, we do not know if 0 is a local maximum or a local minimum using the second derivative test because the second derivative test failed. In order to determine if it was a local maximum or a local minimum, we would need to go back and use the first derivative test. One other point that ties into what we have next. Because we had the second derivative is positive, our second derivative at x equals 3 was positive 36, that told us it's a local minimum, which was how I was able to note that plugging it in over here, it needs to have this type of a shape, which would probably tell me it's going to connect all the way up to here. And likely then, just connecting some dots, it's going to keep coming up like this, but what other kind of behavior is there? I mean, certainly it's not just going to be one big line, so what else is going on? One of the things that we are going to run into, we'd mentioned we had potential inflection points at x equals 0 and x equals 2. These are the places where we could have a change in concavity. Those are also important numbers to find out, or they're important in numbers to investigate because they will tell us some interesting behavior. So we already had just some quick guesses that were based in a little bit in part on the critical values 0 and 3, but also just some easy numbers to work with like positive and negative 1. But we also came up with this plot for a potential inflection point at x equals 2, so we want to investigate there. Plugging in f equals 2, we'd have 2 to the 4th is 16, minus 4 times x cubed, so that's 4 times 8 is 32, which gives us negative 16, which is still relevant because at 2, negative 16, this is where we have a change in the concavity. Instead of having a piece that's coming straight down like this, it tells us the behavior that this is clearly concave up, so it needs to connect and stay concave up. And from here, this needs to be concave down. So you see how the piece I'm having? If I curve it too much like this, then I kind of have to start curving it back upward. And you see how I'm getting concave up? It lets me know that I cannot have this type of curvature right here having concave up because we do not have an inflection point there. Knowing the behavior of the inflection point allows us to put in pieces that would say it's got to have a curve coming up like this coming into our second critical value. Now, a lot of the points aren't matching up perfectly because I don't have a correct scale. I mean, if this is 3, that's clearly not negative 23 right there. I mean, this is not a gap of 20. So not having a correct scale is going to throw pieces off. Anyhow, we still need to do some investigation as to what is going on at 0. Is this a piece where it's turning around? Because this is still concave down. It fits with what we already knew. Or is this a piece that will still remain concave down, but just have a behavior like this? What's going on? Well, we also have to note we had another point for x equals 0. This is another inflection point. So the fact that this is 0 for an inflection point is telling us at this location it needs to change from being concave down into being concave up. Well, we can see this is what concave down would look like. If it's going to look concave up, then it needs to have this type of a behavior. So it tells us then this has got to connect. And you'll note when we're looking at the tangent line as it's approaching, we're getting our horizontal tangent line, which we know should have happened already because the first derivative was equal to 0. And it turns out that the second derivative test failed. Where the second derivative was equal to 0, we didn't know if it was a local minimum or a local maximum because it's neither one. It's a critical value, but it's not a minimum, it's not a maximum, it's just an inflection point. And so we have a rough sketch as to what the graph would look like. And to help prove our point, here's our graph. You can see it's obviously a much better scale, but we get the rough picture as to what the graph is seeing. So all things combined, major things that we are trying to be able to use. The first derivative will tell you where the function is increasing or decreasing. The second derivative will tell you intervals of concave up or concave down. Beyond that, you can use the first derivative test to figure out where you have local maximum or local minimum. You could also use the second derivative test to identify your intervals for local minimum or local maximum, your intervals, your locations for local minimum or local maximum.